Okay, so today we are going to do a bit of hands-on, like I have already said, on metrics, evaluation metrics, and the different ways you can use evaluation metrics. And then after that, we will take a little bit of time to also um, just to help with anybody who may be having issues or challenges with the previous task. I would like to run through all of them and point out a few things and a few mistakes that most people have made, especially in this. Well, okay, I will not point out this last one because I've not graded everyone, but yeah. Okay, so last time we talked about metrics. How do you measure or evaluate the performance of your models after you have trained them? And we also looked at a whole lot of different ways of doing this. And I'm going to kind of run us through them, quickly, right? Just kind of like um so kind of like a recap that will help everyone to be on the same page in terms of how we would the hands-on which we are going to do now. Please confirm for me if you can hear me with a thumbs up, and confirm for me if you can see my screen. All right. Thanks. Okay, so just as a recap, um, we talked about loss functions and metrics. We talked about model search and optimization, and we're going to do a bit of hands-on. We talked about cross-validation and the bias variance trade-off. So we are going to do model search with sklearn at the end of it when we have done a bunch of comparisons. We looked at loss functions and we were able to differentiate, between what is a loss function and what is a metric, right? We understood why we need loss functions. Loss functions are what you use to um, identify how far away each the predictions of your model is from the true value. And it also helps to calculate the gradient and determine the direction that you adjust the parameters in order to come closer to the true values. And we were also able to look at what makes a good loss function. The good loss function has to be differentiable, it has to be smooth, it has to be reflective of the actual goal, and it should be able to handle outliers. So a general formula for loss function, which is basically the sum of the loss for each data point, right? Um, and well, the sum divided by total number of data points. So that's effectively the mean or the average. We looked at different kinds of losses mean squared error, which is the square of the differences, right? The error itself or the residual, the sum of the squares divided by the total number. So the mean of the squares. Mean absolute error, we looked at that as well. And then we looked at the Huber loss, which is the combination of both. Then for classification, we looked at the binary cross entropy, which is a log loss or negative loss likelihood, which is used for binary classification when there are only two classes in the category. And then we also looked at categorical cross entropy, which is used for when there are multiple classes in the categories that you are using for classification. We looked at hinge loss, which is used for support vector machines. Of course, we then went on to talk about evaluation. So evaluation is different from loss. You use loss while you are training the model. You use evaluation after you have trained the model to test how good the model is performing on a different test set. So when we when we're doing evaluation, right, we now look at the things that matter in evaluation. So of course, evaluation helps you to know how your model will perform on unknown or unseen data it was never trained on. That is precisely the definition of generalization. So when you say generalization, what you're actually saying is that this model, I trained it on some data, and then I tested it on data that it didn't see at all, and it was able to come really close in its prediction. So that is a very good example of generalization. Then we also talked about the fact that when you are doing evaluation, the things that matter are not the same as when you are talking about loss functions, right? In evaluation, what matters is how well does it measure or the evaluation metric align with the business objectives. So we are no more talking about smooth differentiable functions, right? In this context, it doesn't really make much sense. But rather you talk about how good of a measure of how well this thing will perform, you know, for the specific business case or business use I want to bring it to. So, and then you see that some metrics highlight different kinds of errors. So we looked at the the two main types of metrics that we use. We have metrics for classification, and for classification, we looked at accuracy, recall, precision, and the F1 score. So accuracy is basically a measure of how much of all the total predictions that that model did, how much of it was correct, true positives plus true negatives over divided by total predictions. But for precision, it is how much of the total proportion of true positives or how much of the total number of predictions it made and gave a positive value, how much of it was actually correct in terms of being true positive. So that's precision. So that gives us a measure of how well models are able to predict the correct true value. But recall is of the total true positives and false negatives, how much are true positives? So recall is like a way of measuring how bad it is, how bad the model is in predicting false negatives. A false negative is when it is saying something is not true and it is wrong, right? So that's a false negative. Then the F1 score is a combination of that. So it gives us a balanced metric that you use to, look at both the precision and recall at the same time, so that's F1 score. Then for regression, is almost the same thing as what we use for loss. The only difference is that we have this additional root mean square error, which is just the square root of the mean square error. So that is to make it more amenable to outliers. An outlier being a value that's too far away from the correct value. So we looked at differences between loss and metric, and you use loss during training, you use metric after training, and all of these other ones. So we also talked about stopping conditions. So a stopping condition is basically something that you use to determine should I stop training or not, right? And this is a very important and key point because in all of the tasks that I have graded, I have seen that a lot of people did not know when to stop, right? One thing again I want to reemphasize is that this class is about training models. It's not really about writing code. So your knowledge is not really about Python, right? Or Python programming. Your knowledge is about end-to-end training a model. So one of the key skills you will have will be to know when your model has been well trained, right? And the metrics we talked about earlier are a very good starting point. But sometimes you may say, okay, I don't need to wait until maybe the specified number of epochs. What else can I use? So we have different stopping conditions. Um, so one of the key stopping conditions you would have would be that your loss has hit the minimum value. So if your loss does not go down any further, no matter how many additional epochs you train, that model will not get better. So you need to be able to figure that out. In fact, in some situations, if you train the model further, the loss will begin to rise again, you know, especially validation loss. Training loss will always drop because it's getting better and better on that data that you're training it on. But at some point, it begins to overfit on the data you're training on, right? So at that point, that's the value of having a validation loss. So validation loss is basically calculating loss using a different set of data that you are not using to train that model. So it's a measure of of the generalization of the model, how well it generalizes. And if you see the validation loss beginning to creep up as you continue training, that means you have gone past the point where that model begins to overfit. And so you should stop, right? Essentially, you are memorizing the data set. So other things that would define why you should stop, sometimes you may not have converged, but the additional gain of um, a few extra hundreds of thousands or even millions of epochs will not give you any large benefit because um, the model is already very close to the minimum. So you say, okay, let me stop at that point. Convergence is another one. So convergence is when your model basically gets to a point where the gradients are very small and the loss really does not increase, does not change, does not decrease meaningfully. Like the difference in the loss, the previous loss in the previous epoch and the current epoch is not that much. So you haven't yet hit the minimum point, but you are very close to it and you can decide to stop. So those are some of the indicators. So this is very, very key, a key skill for you as a machine learning engineer who is training models, that you should be able to know when to stop. And you should be able to know when your model is overfitting or when it's underfitting. So this is a summary of early stopping criteria, right, which we had looked at already. And some of the ways that you can implement. You can use a maximum epoch. You can use early stopping based on some metric, right? You can use plateau-based stopping, which is when the model loss is not really changing by a significant value. You can also reduce learning rate when you get to the plateau instead of just stopping. You can reduce learning rate first of all and see if the model begins to learn. If it doesn't, you stop, or you can reduce it further. But at some point, you reduce the learning rate. The learning rate is so low, you know that it will not learn. And then, of course, gradient-based stopping when the gradient is very small. So we also talked about cross-validation, which is a technique for you to evaluate your models by splitting data into multiple test train partitions. You then use for each of those splits that you have done, you use one of the splits as validation and use the rest as training. When you are done with that, you move to the next one and use as validation and still use the rest as training. And so you just keep going like that. At some point, you would have used all of the splits for validation and all of them for training as well. So this really helps with overfitting because you're not just using some part of the data for validation. Yeah, you end up using all of the data for validation. Okay, then we also talked about bias variance trade-off. So bias is the part of your training where the model is not yet able to fit into the data. And this happens when the model is, too small, it's too simple, it doesn't have enough parameters. So in such situations, sometimes you may say, okay, let's either do some feature engineering to add additional higher order features, right? Or just change the model, right? So that's bias. Variance is when the model is too complex, is much more complex than the data. So it begins to overfit on that data. And overfitting means it learns the data perfectly. But when you try data that you do not give to it as training data, it does terribly because it is essentially fitting itself into the data. So in that situation, what you would do is you can add regularization if you're overfitting. You can also add more data. More data, whenever you have a model that is too complex, it means you need to add more data or you reduce the complexity of the model so that it fits into the data. So yeah, so these are basically some of the things you can do. Um, if you have both high bias and high variance, that means, well, you are in for a bad time. So you have to really do feature engineering or use better representation of the features, right? So so we also saw how you can use cross-validation to reveal bias variance problems, right? So if you use cross-validation, you will always find that a high variance will lead to high training accuracy or low training um, loss, but it will have low accuracy on validation, right? But for a high bias, that is a model that's underfitting, you find that it has a low training accuracy and also a low validation accuracy. It cannot learn on the training data. Also, of course, it will perform poorly on the validation data. So, but if you have a good model that is well balanced, for the data, it will have moderate to high training accuracy and moderate to high validation accuracy. And then the cross-validation scores are also another thing to look at, right? Um, when you are doing the K-fold, you find that for high variance or overfitting, the CV scores will be inconsistent across the folds. If it's underfitting, you have CV scores that are poor across all the folds consistently. While a well-balanced model, you have CV scores that are similar across all the folds. So those are all simple ways for you to interpret, your data. Then, yeah, I already talked about some strategies to fix such things. For high variance, for overfitting, you add regularization. We're going to talk about regularization when we resume and talk about neural networks. We are going to talk about L1, L2, dropout, and all of that. Those really matter a lot more when you are training neural networks. Then you can also reduce model complexity, use a simpler algorithm, and so on. Um, if you have underfitting, then you can reduce regularization. So, that's the opposite. You can increase the model capacity by adding more features, basically more feature engineering, more trees, increasing complexity of models and so on, right? Or you can add nonlinear. So the nonlinear transformation is basically more features, right? More feature engineering. Okay. Um, yeah, so let's move on to look at a few things that we can actually do um, based on that. Do we have any questions so far before I jump into the actual doing? Okay, so I'm going to start off by I'm just going to start off with a simple um, I want to train a model, right? Um, Very simple model, but a simple model on complex data. And then we will see how um, cross validation can help. Or first of all, we'll look at variance, um, we'll look at bias variance, right? How those work. So I'm going to take this example from the task that we just did because it's a very interesting example in the sense that we have data and we want to predict. Okay. The data I have is on um pause, right? So that's what we use for feature engineering anyway. But I'm not going to do much on the I'm not going well, I will need to do feature engineering, right? But take note that this task um is not a feature engineering. What I'm doing now is not a feature engineering example. So we might touch it a bit later, but this is not a feature engineering example. So let's start off with um, pandas. I need pandas. I need NumPy. I need Seaborn. I need Kaggle Hub. Okay. Then I need to load the data set. So load data set, and then I'll specify the name of the data set. So basically, you can get this from the URL from here. Okay. Um, or maybe I should use a different data set so that I don't skew people's minds. So I'm going to use a totally different data set this time so that I don't um, okay. So we're going to use the California housing prices data set. Let me change the data set. Okay. So this is the California um, housing prices. So if you look at it, you will see um, It's basically the median house prices for California districts derived from a census. So if you look at this data set, you see the analysis that's done on it. You have longitude and latitude, which determine the location of the house. You have housing um, median. That's the median age. Okay, so that's the age of the house. Total rooms in the house, total bedrooms, population, households, um, median income, median house, ocean proximity. Okay, so longitude, latitude, housing median age, total rooms, total bedrooms, populations, households, median income, median house value, ocean proximity. So so then we are expected to predict the value, right? So this you have two files, right? You have this first one that contains the 10 columns, and then you have this one that contains the actual housing cost. Okay. So I'm just going to pull this in. Now, I'm going to start just by to prove this bias variance thing, right? We'll just start by training it with a very simple model. I'll use sklearn just so that it's easy for us to run. Yeah, I need to import OS as well. Okay, os.list directory. So this again is something I do when I download um, from Cargo, because after downloading, sometimes the yeah. So this should be dataset download. Don't mind me, dataset download. Load dataset will be if I have already um, gotten the dataset locally. So it's going to download, and then I'm going to just do a directory listing, right? So so we'll see housing.csv. So we'll just load that. We'll create a new data frame, is pandas dot read CSV. So and then we print that. So that gives us this value. So yeah, we don't need to do too much of we don't need to do too much of um feature engineering. Well, we don't need to do data cleaning, right? Everything here is basically numerical. There's no categorical except this ocean proximity, which is a categorical, which we can just use a categorical. I don't know what are the possible values. If we want to look at the possible values, we can do data frame dot. Okay, let's get ocean proximity. Get the unique values. So you see, you have these unique values. Nearby 1 hour, less than 1 hour from the ocean, inland, near ocean, island. So this will be categorical, right? And you can even see that in a way it is also um it's there is a bit of well, we can use a nominal categorical here, right? But you can also use ordinal because um it also kind of they have relationship in terms of how close they are to the ocean or something. But anyway, we can use a one hot here. So you see that this has a lot of features here, right? So if we use linear regression, we'll get a lot of features. Let me find out how many um let me find out how many rows that we have. So count. So this is a count is 2640. This has 2433, so it does have some nans in it. Um info. So this you can see this one has 2433. Um so basically this has a few nans in it, the total bedrooms. So they and this is a large number, right? So the question will be what do I do? You know, this is a large number. 640 minus 433 is about 207. So 207 rows will be lost if I just do drop now, for these total bedrooms. Okay. So it's an interesting question to ask. I could use some kind of you know, algorithm to say, okay, the total bedrooms is 129 and the total rooms is 880. Total bedrooms is 129. Here the total rooms, this is weird. These numbers are really big. Total bedrooms is 1106. So, but anyway, I'll just drop those 200 just to simplify things. Okay, so if you do that, okay, and then we will look at DF again. So we'll now see that we've lost, it's now 20433. If I do the info again, after dropping those, you now see that they're all 20433. So we'll just work with that. And you can see the data types are all, float 64 and object. So ocean proximity is object. Now, um, so I do need to know the actual prices. Um, yes, we can drop an entire column. But what I want to do is I want to try a few things, right? To see from feature engineering where we can do feature selection, right? To even cross validation and all of that, right? Okay, so I find that I don't think we can use this data set. It doesn't have a target value for us to predict. Um, I'm only seeing median house value, right? Um, but the median house value, well, maybe we can just use the median house value as what the value to predict, because I was thinking we will have that, but according to the description here, it says that the median house value is median house value for households within a block, right? Within a block. So, well, we could use that. So let's use that. just for the sake of trying out some of these concepts. So let's start off first of all by doing um simple. We will have to do this um we have to do this categorical, right? We have to do this categorical ocean proximity. We have to do the categorical one hot encoding, and then we will take this as our Y. So let's start off first of all by um, I'm not going to normalize the median income, um, the median house value. This is actually a large number, but I can see that everything is 6 digits, right? Generally, I could also check the mean. So I could do the mean of um house value, median house value, and take the mean. Right. So it's a 6 digit number. So it's very easy for me to normalize this by just dividing it by um, you know, um 100,000, right? And I get a normalized value. Now the key thing there is that when I want to now get the value back, I can easily multiply it back. So it's for Y values, it's always a good idea to just do that kind of very simple normalization, right? Where you use a factor, a fixed factor, right? So yes, so I take median house value out, I drop it, and that gives me the X. Okay. Then the Y is the median house value, right? So I'm going to then do a bit of very simple scaling with sklearn. So import sklearn. Um, yeah, so what's the criteria for choosing Y? Typically, Y is the thing you want to predict. And like I say, in this case, it's not very obvious, but I just decided to, this is a training, it's for training, it's just for practice purposes, right? So I just pick, because if you want to predict the price of housing, what are you going to predict? It's going to be the value of the house. This is not the correct thing, actually. The more correct thing would have been to predict the price of the house, right? But then the closest thing is the median house value. So I'm just picking that, right, and using that. So right now I'm not doing model selection first. Um, let's get X train, Y train first. Okay. So to get X train and Y train, we'll first of all need to do a normal standardization, import um, um, well, okay, so I need that, but I also need to do standardization. So the first thing I need to do is before we even get to test train splits, we're going to use pipelines. Okay, so let's get pipelines. Pre-processing, okay. We get pipeline, okay. Then We're also going to get, well, we can use um, standard scalar, and then we also get column transformer. Okay, so then let's get a test train split as well. So we use that one we want to train. Okay, so now, so the first thing is I'm going to use pipelines to just pipelines with a simple scalar for for the numeric values. So I'll basically do something like this. Um, pipeline pipeline equals, yeah. So I'm going to create a pipeline with a one hot encoder and a numeric one hot encoder and then a standard scalar, right? Um, so typically, um, it should be able to know that which columns that I am using. Okay. Um, so let's see. Okay. Let's see how this looks. So this is a very simple thing. Now the question is, um, how will my thing cannot center sparse metric says, okay. Um, yeah, I should have done that. Sparse output is false. Taking a bit of time. So what I am worried about is that um, my pipeline may not be able to differentiate between which columns are categorical so that it does a one hot and which columns are you know numerical. So I think I have a situation where I have effectively so first of all, let's see, I took off the median house value and that was my X. I did not do proper on hot encoding on the um, ocean proximity. So I'm going to do this again. So we still have it as near bay, inland. So even though I have passed it through, um, oh yeah. So I don't know how it handled this, right? I'm interested in seeing how it handled it. So let's see. X shape, X transform shape. Okay. So we ended up with a situation where we have 28,109. And that's because we basically turned every column in this nine into a one hot sparse vector. So that's not the correct approach, right? I was just experimenting. Now, the correct approach is to specify which you want to use, which column to apply on hot and which column to apply standard scalar. So you have to use a column transformer anyway. So you first of all are going to create a pipeline for the numeric transformation. So you can say um, numeric numeric pipe. So for this, you just put only the standard scalar, right? And then we'll create another categorical pipe, which uses one hot encoder, right? So numeric pipe uses a standard scalar, categorical pipe uses the one hot encoder. Then you put these two together using the main pipe, which is use a column transformer. So the column transformer, right. So this is the long list of all the columns that have numerical values, right? Um, so you specify that for these columns, right? For this long list of columns, okay, I want to use the numeric pipe, which the numeric pipe only contains a standard scalar. And of course, this is just a name. So in pipelines, by the way, in the convention in SQLN pipelines is that you always provide the elements in the pipeline or the pieces in the pipeline, you always pass them in as a tuple, right? In this tuple, the first will be the name that you want to identify it, and then the second is the actual class that will execute or will transform your data. So that's what this is. So even in the column transformer, which is also a kind of pipe, it's a pipeline as well, you're going to specify the name that you want to give to it, and then the actual, class that will do the transformation, which is the numeric pipe, and then you specify which columns. So for column transformer, the third parameter you have to pass for each of them is which columns you want to do. So for categorical, it's only the ocean proximity column that I want um, to use to do categorical. So that's what I should have done. Okay. Then with that, I can just run, I can just do a fit, right? Let me see if I just do a fit that way, whether it works. So I'm going to restart. So now, so I have X transform, but I want to see. So you can now see that I have 13 now. So the reason why I have 13 is I have 9 as the original features, of which one of them is categorical. Now that one that is categorical, if I remove it, I now have 8. Okay. Then that one that is categorical will get transformed into a one hot encoding. Now, because the categorical itself has how many unique elements? So let's go count. The number of unique elements in ocean proximity is 1, 2, 3, 4, 5. So it's 5. That means the one hot vector to represent them has to be 5 elements. So if you add that 5 back into the 8, right, you get 13. So effectively what has happened is that I have essentially converted the remaining the first 0, 1 to 7 are the same as this first. Okay, let me do this. Let me do the X and show you the X as a data frame first, right? X is still a data frame. So you see that here you have 1, 2, 3, 4, 5, 6, 7, 8. So these 8 are still there, even though they have been normalized now because we use a standard scalar, so they have been standardized. And then the remaining one is the one hot that represents the 5 categories. So you see that this near bay, near bay, near bay, near bay is in which position? Near bay is the first. 1, 2, 3, 4, 5. It's actually first here, but our one hot encoder put it at this end. So anyway, so we have this. Now, let's do a simple training. So to do simple training, let's use a simple linear regression, right? So we do simple linear regression. We get a mean squared error. Now, I'm going to use the mean squared error as our loss function. Let me see if I can get a root mean squared error. So we use root mean squared error for our metric, okay? Then we now do a simple training on this model. So um, we can say model equals, so we'll create a new linear regression model and we basically train. Okay, so first of all, before we can do this, right, let's do our XY split, which I forgot to do. So you have X train, Y train, X test, Y test. For now, we're going to use the X test and Y test. We use train test split, which I had imported earlier. Okay. So we split with this test size of 0.2. That is 20% of our data set will be used for testing. Okay. That will be the X test and the Y test, while the remaining 80% will be used for training. Now, so if you look at this 20%, this 20%, if you calculate 20% of 2432 or of 2433, right? If you just do a simple calculation, 20%, um, 0.2 times x dot shape 0, which is you know, so it means we are going to use about 4086, right, for testing. Then the remaining 18,000 or 16,000 or thereabouts, we will use that for training. So if we now, let's do it, just looking at the shapes, X train, shape, Y train, dot shape. So we'll get all of that. Just, okay, we don't have that yet. I need to run this first. Okay. So you will now see that X train is 16346, right? 4087. While the tests, um, hold on, I missed something. X and Y should be the same, so I think I missed something. Test test train split. Um, so the resulting value should be, I mixed up the it should be train and test first, X train and X test, then Y train and Y test. Y train and Y test. Okay. So with this, you will see that X train and Y train have the same number of rows, but this is 13. So we are talking about 13 features now, okay? So we now initialize a linear regression model, okay, and train it, okay? Then after training it, we can then just do simple prediction. So let's just do a simple prediction. with the X test. Okay. Now we can calculate the cost function. Um, so um, basically for the matrix, so we can use the mean squared error. Okay, so we can do let me look at that mean squared error. Okay, so when you're doing mean square error, you pass the tests y and then the predicted x test. And um, this is a very high error. Let's do that for y train. Okay. So okay. So the main thing you see here is that this is a very, very large error. This is a very large error. Like this to train. You see that um you actually see how basically you see how it tends to just train and then it has a built-in stopping um condition, so it stops, right? And it stops because the change in the loss is very small. But you can see that this is not doing a good job. If I want to do a plot, so let's do some plots here. Figure, fixed size. Um, yeah. Let's see it for then dot subplot. Okay, 1, 2, 1. I don't know. It's bringing heat map. That's not what I want to do. So I'm going to plot a scatter. Yes, I'm also going to do a plot of Y train. So this is first of all just um I'm trying to do a plot just to show how close is our regression model in predicting um in terms of how well is it even predicting. So you can see it's well, first of all, everything is all scattered, so there's a whole lot of noise here, right? So it's going to there's going to be a lot of error here. This is actually not a really good data set for you to do this. So you can see how the prediction, well, it is a good data set. I think, let me take that back. What I was going to say is um, let's do a second subplot. So this one, so the red dots are predictions by our model, while the blue line is the correct, perfect prediction. Our model is very far from it. It's a lot of, um, that's why the loss is so high. The mean square error here is very high, right? So if we were even trying to do like um model selection, right? You find that already this is very, very high. So this model is not going anywhere, right? And that's where when you talk of bias variance, So if I were to plot, let me finish plotting this. So this is now with test. I want to now do with test, not train. So the whole idea, what I'm trying to achieve here is to show you this is a model that, so even on the test, this is the test data and it's not doing very well at all. And this is on the train data. Okay, let me also do scaling on the Y values and see if it would fit better. So typically scaling on the Y value doesn't really help much, to be honest. But we can do that. So to scale Y values, I'll just use a fixed factor, right? Like I said, 100,000. So we can just say Y equals Y divided by, um, so Y is still a data frame. I wonder if that will work. Yeah, it should. Okay. So let's rerun everything again. Um, we've already loaded the data. I'll just start from reading PS, reading from here. So read the CSV file, get the data frame, drop the not available values. Um, we get the X and the Y, ocean proximity Y. We do the scaling for X, right? Um, okay. Oh, I had done this already. The test train split. So let me just delete this. Um, okay. All right, so I have scaled Y. It should really have been divided by 100,000, but I don't know how I managed to skip that. So, but anyway, Y has been scaled by 100,000. So if you look at Y now, I've basically scaled it to this. All right. Um, so we will do training again, fit, and then predict. So we now have lower values for Y. We have lower error. We have lower error here. Now let's plot this. So this is like I scaled Y, but it doesn't make a difference, right? We have lower values, but it doesn't make a difference. So actually scaling or standardizing Y doesn't make any difference. The problem here is that this model is not good enough. Now, um, we could try a bunch of other models. For example, I don't know what model would be good enough for this. We could try a random forest, right? We could try um so essentially if we were doing I don't even need to go to do cross validation on this. It's just too bad. I could try instead of a linear regression model, I could try a polynomial regression model. So let's see if I try a different kind of regression model. Um, let's see. We can try an SVM, right? SVR. So SVR is a support vector machine for regression. Okay. So again, this is the beauty of sklearn. It's very easy for you to just swap out and drop, drop things in. So it will be very easy for me to um just replace my linear regression, right, by bringing in the SVM and then specify the SVM specific um argument. So let's do that. Um, okay, let me do this. Let me do this separate. Let me do this separate. Let me do this separate. So let's use support vector machine. Okay, so with support vector machine dot svm import svr. So we're effectively bringing in a support vector regressor. Let's see how well this does. Um, so we first of all do the model equals SVR, right? We could put a kernel in there. Well, by default, the kernel is RBF anyway. You can see that we have a third degree gamma scale. So let's just simple SVR, and then we fit. And then we are going to do the same thing that we did. We are going to see, we're going to calculate the mean square error based on that for Y train and for Y test. Well, I could just plot this, right, so that we see rather than, the mean square error just gives us a single value. Okay, so let's fit using a support vector regressor. Then let's plot now. So we are basically plotting the same thing, Y train, then Y train against the predicted value. So this will give us visually how well the model is doing with the training data. Then we'll do the same thing with Y test, then Y test, and then we again predict with X test. And let's see how much, if it's doing any better using, you know, SVM. So, well, we see that SVM, it tries to match a bit, but um, there's still a lot of error here, right? A lot of outliers, but at least it's better than this one that was not even kind of following the trend, the general trend. So we can do this for a bunch of different models just to see which model will give us the best. So we could take a model, let's try random forest, same thing. Okay, so let's try the same thing with the random forest. Uh, Random forest may not be that good, right? But let's just try it. So from a scale um so random forest is in the ensemble. So we get a random forest regressor and we do the same thing, right? Again, default settings, right? Number of estimators, number of trees in the forest is 100. Maybe I can increase that later on. The criterion squared error, and so we run fit again. Now, again, I'm going to do this to see how well it does it. This is taking a bit longer. Random forests are really good for simple when the data is not a lot, right? Well, this is 200 right? 20,400 and something. So I'm even surprised that Random Forest was able to get something out from it. Now let's see how well this one does. So you can see the Random Forest is performing much better than this. If you wanted to calculate a metric, like just calculating the mean square error, you will see the difference. And we can always do that. We are going to do that. Okay, I did not give the model different names. So I'll run that with different names. But I always like to plot it this way so you can see a visual. You see, this one, the band is much smaller. So the random forest is doing so well on the data that you gave it to train on. But on the test data, you can see it's still kind of scattered out. So this is a good indication that what we call is underfitting, right? It's doing well on training data, but it's not doing so well on test or validation data. So in that case, what I will do is increase the number of parameters. So let's increase the number of parameters in this random, the number of trees, even though it's probably going to take longer, but let's say maybe 300 trees. Um, so how you specify that is number of estimators. Okay, so I'm going to rerun this with 300 estimators. It's going to take a bit longer because, of course, there are more estimators. Now, if we had neural networks, it would be so interesting for you to see how well neural networks would perform on this. But we are not there yet, so I'm not going to bring that in. So what I will do is maybe like do a plot of what you would call bias variance plot, even though I'm using different model types rather than doing rather than using the same model type but with multiple or different um, configurations or different parameters that would make. So that would be the best way for you to demonstrate how models get better, with better. So this one is 300 trees. So here it's clear that it's also performing better on the trading set because it's coming really close to predicting this perfect straight line. And you can also see even in the test set, it's still not as good as training set, but it is definitely better than when we had 100 estimators. So this is kind of an indication that um, with more parameters, with more complex model, you can actually get more, you get better performance if you get less overfit. Now, the other thing we could do is feature engineering, right? So if I do feature engineering now, what kind of feature engineering could I do? Longitude and latitude, right, are two separate numbers, but are they really separate? Okay, that has to do with, um, it's geometric or geological location, right? Um, Total rooms, total bedrooms. We could even remove some of this. So this is an interesting thing. We are going to try this now, where we could say, um, when you are using SQL, there are many ways you could use for feature engineering to kind of reduce the number of features, right? So one of the ways that we talked about was using um there were many ways, right? feature elimination, right? Recursive feature elimination, that's RFE. So let's see if we can use RFE to identify which features, you know, don't really contribute to this prediction. So let's see. We get RFE from sklearn. Let's see. Um, let's do this from sklearn. So we have a feature selection. RFE. So RFE is recursive feature elimination, basically. So what we are trying to do is we want to see if we can run RFE on a random forest, or maybe we run it on a linear regression model first. There is also polynomial regression, which we have not looked at. So let's do polynomial polynomial we could do let's try polynomials first before we do the RFE. So there are two ways we could do it. One, we could use a random forest and use a polynomial kernel, right? So yeah, so I'm not seeing kernel as an option here. Oh, sorry, SVM, not SVM, not random forest. Okay, so kernel is polynomial. Polynomial kernel is just poly. I'm also going to start changing the names. So I'll use this as SVR. I'll use this as SVR so that I can continue to track them. Okay, so we have SVR now trained with a polynomial kernel. It would, well, I was expecting it to do better, but it doesn't seem to be doing any better. Um, support vector machine. Okay, we could also do a polynomial um regression with sklearn, right? With using a polynomial regressor. So so for this, so for sklearn, what you can do is we will apply polynomial features, right? So we'll do polynomial feature engineering. For the category, there is no polynomial um there's no polynomial relationship. So I'm going to skip that for the for the categorical features, but for the numeric features, I'm going to add, in addition to the standard scalar, after the standard scalar, I'm going to add a polynomial feature to it. So that would add some additional polynomial features. Okay. Right. So effectively, I have rather than trying to use a polynomial equation to model it, I basically use polynomial features and then still run a linear regression. So remember when I said that you can actually do that and um use for linear regression, you can improve its performance by using polynomial features. So that's what we just did. Now, with polynomial features here, you can see that, let's see how a linear regression model now does. Well, it's not as bad as before. It's still not as good as the others, right? But it tries to fit better than before. Okay, so let's do RFE. Um, our SVR is still running. We will now do RFE, which is recursive feature extraction. I'm going to just do that with, so the interesting thing is we have polynomial features now. So the number of features have increased, which is why, let's see, if you look at the shape, you now see that we have 50 features because the sklearn polynomial feature um, class or function has basically taken, we had 13 before. Now, of those 13, um, 5 were the one hot. So the remaining 8 have been, changed. It's been increased to 45, about 45 now, because of these 55 are still one hot, right? 5 of them are still one hot, and the remaining are the polynomial. So 45 of them basically have been turned into polynomial. Oh, you can see a bias term was added, right, at the beginning, once at the beginning, and then a whole bunch of additional, values were added, which are kind of higher orders of the original value. I probably should have normalized after the polynomial features, not before. So yes, so let's do that. So in this pipeline, because what has happened is the polynomial features introduce ranges that are either too narrow if the numbers are below 1 or too wide if the numbers are above 1. So you still need to normalize. So it's better you do the polynomial features before you normalize. But the concern I have now is we can have numeric overflows. Remember, the numbers are already huge. So you have big numbers like 7,099, right? And so on, 2401. These large numbers, um, 2401. If you use polynomial now, if you square these numbers and cube them, they will become very large. So it's probably a good idea to then do a 3-step process. We first of all do a standard scalar, then you do a polynomial, then you do another standard scalar. I don't know if this is a nice idea, right, to stack scalars, but let's just see what happens with this. Okay, so I'm going to run again. Okay, we're still waiting for this. So I'm going to stop and rerun it. So the column transformer is used for you to apply different transformations to different parts of the pipeline. Standard scalar 2, standard scalar 1. So you use it to basically if you have different transformations you want to do on different columns, then the standard scalar is what you use. Okay, so I have introduced transformed higher order polynomials, and then I still did standardization on those transform values so that they are still within a range. Then I run linear regression, and the linear model does much better, right? Due to adding polynomial features. Now our support vector machines is taking a bit of time. Okay, so while this is running, because we are kind of running out of time, I'm going to try to point out a few things that I have noticed. Um, right. So this is an interesting one where you can see that because of the polynomial features, the training, um, you see the training performance of our support vector regressor is, well, not that good, maybe because there's a lot of data, but you can see how the validation of the test is doing so well, even though we have these outliers, right? But it tends to be doing very well, coming close here. It's really the outliers that are making it look wild. So this is the benefit of adding polynomial features, right? The same features will apply to, they will all benefit from it because this is feature engineering. We didn't just, it's not just changing the training, it's a feature engineering. Okay, so um, the random forest will also take a bit of time as well. So while it is running, I'm going to make a few comments. So the first thing I noticed, like I said earlier, a lot of people don't pay attention to requirements. So I think I've already said that, so I'm not going to dwell on it, but remember to always look carefully at the requirements in the task. And every single requirement must be met. It has to be done. If your score is not 100%, it's because you did not meet at least one or more of those requirements. That's the first thing I've seen a lot of people, the mistake that people are making. The second is if you are training a model, train the model to converge, right? And look for ways that you can measure the performance of the model. Of course, that's what we are doing today. So this is one of the ways I use, like just a simple plot of Y train, Y train. You plot it as a line. Then you do a scatter of um, Y versus Y, right? Then you do a scatter of Y versus Y pred, right? Or Y versus Y hat. That will show you how far away your model is. From this blue line in the middle is a perfect model. If this model were perfect, all of these red dots would be exactly on this blue line. There wouldn't be any red dot spilling out anywhere else outside of this blue line. That's why you see that this one is a very good performance because all of the red dots are almost exactly on the blue line, even though you have a bunch of outliers. This is for me like very easiest, graphical means of viewing the performance of your model. All right. Now, there are other ways you can also view the performance of your model, apart from um, so calculating test training loss and validation loss or test loss. What I actually did here was basically plotting the same graph for training data, right? Training X and um, Y, right? Or predicted training Y, rather training Y and Y pred, right? And then that's for this chart. Then this second chart, the one on the right, is the test Y and Y pred. So you see that um, you see that it's even doing better on the test, which is interesting. Um, for a random forest, I'm still waiting for this. Because of the number of features, right? And the number of estimators, you see it's taking a lot of time. So that's one of the things that we talked about with random forests. Okay, what else? So number one, pay attention to requirements. Number two, um, ensure your model converges. Number three, give me a proof that you had an input in the process, right? A lot of people just go and carry AI stuff and come and dump. I don't even understand what you are doing, right? So it is very, very important that you understand what you are doing. That's what I'm trying to train, everyone or kind of set that mindset. You have to understand what you're doing. Even if it is, you ask or you outsourced it to AI and ask AI, okay, do this for me. Like I'm sure some of you notice sometimes I start typing and the AI does autocomplete and I accept. But sometimes I accept and that's not what I want. And I correct it. So the idea is demonstrate to me that you have done some thinking of your own. And one of the ways to do that is to give me a summary. That's why I ask for text block above every code block. The text block is a way for you to prove to me that you understand what is going on, right? And you are in control of what is going on. A lot of people are not doing that. I notice a lot of people who duplicate code multiple times that are doing just the same thing. So why are you duplicating code, that does the same thing? Why are you running the same training loop at different parts of your repeater notebook? If the issue is that you don't understand, by the way, for your information, anything you do at the beginning of this, from the beginning of this Jupyter notebook all the way to the anything you do here is still, you are still able to access it later on, right? Any variable you declare, any function you declare, and so on. So you don't need to repeat stuff. Okay, so that's another point, I want to make. So take time and stamp your own presence or authority in the work. Okay, that's what I'm trying to say. Okay, now the random forest regressor is done, and it's beginning. Well, it looks like it's doing very well on the training data, and it's still kind of not doing so well on the test data. Okay, so let's try RFE. So with RFE, um, it's basically eliminating features that maybe there's no correlation at all, or two features that are correlated too much. It removes, one of them. So the way to do this, right, was basically to do some um you would do a regression model. So for example, with this one now, I want to do a regression model. So I will do a model. So let me put RFE equals, you create an RFE, but you need to also pass into it a model that you will use, right? A model that you will use. Um, so you have to specify an external estimator that assigns weights to features, right? So a good example is basically to use a linear model. The linear model um, will give you the weights. So a linear model will generate weights for this. And so let's use linear regression. Okay. And then we still fit. Um, so if you run this, right, it's going to take a bit of time. Okay, that was quick. Um, so now, for us to be able to find out what RFE did after it has run through all of the features, um, we can do this. Um, First of all, let's look at the ranking. So we can the feature ranking is RFE. Ah, well, okay. So um, let's first of all, let me first of all show you what the RFE ranking does. Right, RFE. RFE does support. This is first. Um, so this is kind of a mask. A feature is a mask that masks out certain features, right? So the true ones are the ones that it considers that the features are good, right? And um, the the false ones are the ones that. So what you normally can do is just use a data frame because this is basically a feature mask, right? So you can just do a data frame and pass this in as a mask to the data frame. So something like pandas df selected. The selected features would be the create pandas data frame. Um, so you specify the columns, which are the values of X. Sorry, the columns of X. And then support, like we have seen, is the ones that, okay. This is not really what we can do X dot columns, X. Okay, then, so this is all the X. But now, when you pass this RFE dot support in, it's only going to give you, um, oh yeah, okay. So, I need to get the columns. Um, I need to get the columns. So, okay, so these are the columns. Okay, the only challenge is that this is now um, this is a transformed column. So, I won't have the names anymore because um, yeah, so I won't have this. But so at the end of the day, right, this just tells me which of the columns RFE finally selected. That is column 1, 2, 8, 32, and 47. And that corresponds to from the original transformed X, right? These are the columns. The reason why I don't have the column numbers anymore is because it has been transformed. So let me see if there's a way to print that. So X, let's just make a data frame from it. Yeah, let's just make a data frame from it. So what it means is that column 1, right? Column 2, column 8, um, column 32, and column 47 are the ones that are really relevant. Let's do this with a different value. Let's do this with just X and Y, right? Instead of um, X train and Y train, because if I do it with X train and Y train, I'm not really going to be able to show you. Um, if I do it with X and Y, at least I'll get the values back. Okay. Oh yeah, I did not remove the okay, let's redo this with let me do X transform, but without the second. Let's remove this polynomial, the polynomial scalar, right? Let me do this whole pipeline, but I will not use the polynomial scalar. Polynomial scalar is not allowing me to see the original columns. There are too many new columns. So let's ignore that for now, and let's just do it with yeah, let's just do it with standard scalar. So we're now going to get a new X. Let me just call it XT. Um, or let me just call it X underscore. So we have a new X that I use a standard scalar, one hot encoder, and we'll start from here again. Then we're going to do the RFE fit on this X and Y. The Y will still work. Um, uh, okay. It should be X underscore. It should be X underscore. Okay. So now this now corresponds to the original columns that we have. So it will be very easy now for us to see which columns were it's easy to see which columns. So you can just you can do a pandas data frame from X, right? And then it will be easy to see which columns. So we still have 13, even though the ocean proximity now is a one hot. So we can get the categorical column names for ocean proximity. But I'm going to do I'm going to do this. Um, so these are the columns 1, 2, 3, 4, 5, 6, 7, 8, 9. But this ocean proximity is now replaced with 5 additional columns. But if you just look at this, you see that anyone that is true here maps to the same thing here. So what it means is that the RFE support, right? RFE support gives you which columns finally were considered as important, right? Um, Let me do something more. Columns dot X. Okay. Let's remove the drop. So let's drop a column. Um, column columns equals. Let's drop the ocean proximity. So okay, then we will concat. So let's just turn it into a list. Um, as to lists. Let me just simplify this. So we get the columns to list, and then we add ocean proximity. It's actually not ocean proximity. It's more like ocean proximity 1 to 5. So this is just a rough way of doing this. I'm sure if you go do, there are much better ways of, you know, doing this. Proximity 4. Proximity 5. Okay, so I now have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So that matches it. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So if you do that matching, you see that longitude is true, latitude is true. So that means longitude and latitude are features that remember RFE had eliminated features that are not very relevant, right? So the ones that are left with the value of true are the ones that really contribute. So true, true. Then that is 1, 2, then 1, 2, 3, 4, 5. After that are not. So the housing median age, the total rooms, the total bedrooms, that's 3, population and households did not, you know, really affect then, but the median income affects, right? Then you have false, true, true, false, false. The ocean proximity 1 did not have any effect, but proximity 2 and 3 have an effect, and 4 and 5 don't. 2 and 3 are the one hot vectors that basically encoded. If you go back to look at it, the one hot vectors that encoded the 5 different um, states, how close it is. And this is 1, 2, and 3. So 2 and 3 is this two. I don't know what this corresponds to, but I can see that inland and so on. So this is just showing you if I've done this, I can now take the X, right? I can then take a subset based on this selected, right? And use it to train my model. So instead of training using, this should be underscore. So now instead of training using, I'll train with only the ones that the RFE has identified as the features that really matter. 1, 2, 8, 32, 47. Or in this case, I didn't look at the numbers here, but I can easily do that by just well, it's still going to be the same thing. RPD PD data frame X. So let's do that here. PD dot data frame X, right? Dot columns RFE dot support. So that will give you again range index. Oh, sorry, this should be square brackets. Okay, so this gives you the indexes that matter 0, 1, 7, 9, 10. That matches is 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So if I use the values of X in these indexes only to now fit my logistic or my linear regression or my linear regressor, what it's telling me is that I'll get a better correlation. So let's see if that works. So I'm going to do X relevant or X selected. Okay, I like that. So X selected. So X selected, we are going to take the X that we have done and we take all the rows, but we only take the columns that RFE had come up with, right? So we'll now use that to basically still train a linear regression model. And then I fit. Now I'm going to come back and do this to see how well it performs. Because again, remember, this is just what I'm using to see how well. So let's see what I get. Okay, so this is not correct. I should be using Y. Should be using Y. I'm not going to do train test. I probably should have done train test, right? Okay, so let's do train test split. I forgot to do that. So I'm going to do train test split. So X train X selected train. Well, these are getting very low. Train. Okay, X selected train, X selected test. So I still do the same test train split. So I'm going to train on X selected train. So again, remember, I'll use RFE to eliminate and to select the features that matter most. Now, I now pull only those features that matter most from here using this, right? And then, um, okay, so this should be Y train. So I now fit with the selected values. I still split the selected features, right? I still split it into test and train. And then I train with that. And then I'm going to use Y train, but this will be X selected. And the model I'm using is the linear regression model. Okay, same thing here, linear regression model and X selected. So this is now with, well, I was expecting it to do a bit better, but the fact that there isn't that much difference, right, just tells you that in a way, RF has demonstrated that for the linear model, right, those features are really the ones that matter most. So this is the most important aspect of it. Okay, so I'm going to pause there, right? A lot of these things are just they might look like they're a lot. It's because I'm actually packing in so many things and I'm not really answering questions. I'm basically just trying to throw ideas out. But what I was trying to do today was to show you how you can use evaluation metric and also combine it with feature selection approaches to kind of improve or select models. We will still do more of this, right? Because there's really a lot here. I was trying to show you, first of all, let me recap, right? First of all, I first started off by downloading a data set that has housing pricing. I found out that the data set does not have a y hat for me to predict. So I picked a particular one, the median house value, and I used it. Because of that, that's why we tended to have very low correlation. But nevertheless, I still went ahead and did a bit of feature engineering here using a standard scalar, using a polynomial features to add additional polynomial features. And then after that, I did a second standard scalar just to scale the new polynomial features I had added, right? That's the essence of this second one. And then we have a categorical pipeline that uses a one-hot encoder. So I made two different pipelines. This first one is just for the numeric columns. And the numeric columns here are the longitude, latitude, housing median age, total rooms, total bedrooms, population, households, median income. And the median house value is what I use as my Y. Okay. The ocean proximity is a categorical feature. So what I did was for that one, I created the categorical pipe and the categorical pipe, which is a pipeline basically, and I used a one-hot encoder. Now, if you remember, a one-hot encoder is one of the ways you use to encode categorical values. So now I use a column transformer. What the column transformer does is that it allows you to decide which of the columns, by columns, we mean which of these features. So this is one column, longitude is one column, latitude is another column, housing median age is another column, total rooms is another column. So column features is the same thing. So what we are trying to do is with a column transformer, you now want to decide which of those columns should you apply which of these pipelines, right? So remember, I have two smaller, I'll call them sub pipelines. I have two smaller pipelines. So I'm using this one to scale numeric values. I'm using this one to scale polynomial values. So a column transformer to map which one should go to which column. So the numeric pipe line should go to these columns that I've listed here. So you see this list of columns here, right? Which is basically all the columns I had identified. In fact, it might be easier for us if I just cut it off and call it numeric columns or numeric features so that it will be easy to understand. Because so let's call it numeric features, right? In fact, the AI has even completed it for me so that it's easy for you to, for everyone to understand, right? That I'm just using this to, identify the numeric columns, right? So, or the numeric features. Same thing here, the categorical features. So I guess it's easier to understand it this way. So we are now using this column transformer, which is still a pipeline, to now allocate and say for the columns that are in this list of numerical, so for all of these columns here, right, apply the numeric pipe, which is the numeric pipeline that does standard scaling, does polynomial features, and another standard scaling to still further rescale the polynomial features. Then for the column that we have identified to be categorical, which is the ocean proximity, right? This is saying apply the categorical pipeline or sub pipeline, which just does one hot encoding only to the columns in this, and that is only the ocean proximity. So I now end up with a pipe that is made up of other pipes inside it. That's how powerful the SKLN pipelines is. It's something I'll encourage everyone to go and check out and study. So I did two pipelines. I put those two pipelines inside one pipeline, and this one pipeline here is used to allocate. So if I actually take this pipe and I kind of dump it, you will see how it looks like. This is how it looks like. You can see this is a visual representation, the column transformer, right? Which is a pipeline that is made up of two pipelines, the numerical pipe and the categorical pipe. And these are also two pipelines. So this is a very good visualization of that. So after that, I run that pipeline on the original X value that had these original columns here and had the original, you know, this is the original X value, right? This is the original X value. So when you run fit transform, the pipeline will essentially run the normalization for you and the categorical encoding. And this resulting value, X transformed or X transformed, is the new X, where both the standard scaling has been applied, plus even the polynomial, plus even the categorical one-hot encoding. So that's why X looks like this. And this is X transformed that I turn into a data frame. You will see that the number of columns has increased because of the additional ones that were introduced by the polynomial feature um, um, improvement. Polynomial feature always increases the number of columns because it basically adds additional columns, and those columns would now be higher order values of the different X or the existing features. Okay, so with that, I now have the feature engineering part done. So literally, actually, what I was doing here was feature engineering. Now, at this point, I now want to do some regression. So I run linear regression. I then now plot two versions. Here, I'm trying to demonstrate two things. The essence of a validation data set. The validation data sets that we have is achieved by this train test split. So you take the original transformed X data, you split it. So you're now going to have the training X and the testing X. Remember, the number of values in X transform has about 20,640. It actually says here is 20,433 rows and one column. So of these 20,433 rows, I pick 20% of it, 0.2 of that, 0.2 fraction of that, right? Which amounts to about 4,087. Just that number of rows is what we will use for testing. We reserve it. We keep it aside, right? We don't use it to train the model. We keep it aside. After we have trained the model, we will use it to run evaluation and calculate the loss. That is evaluation. Then the remaining 80%, which comes to about 16,346 rows, is what we now use to train. That is the X train, right? 16,346 by 50 columns. The 50 columns is now because of the categorical plus the polynomial features that we were adding. For the Y, we still have the same number of rows, but exactly one column. This is train data, while this is test data. So for test, we have 4,087 rows, much less, but the same 50 columns as the X, that's the X test. And then the Y test is 4,087 rows, right? And a single column. So that's how you separate your data into the set for training and the set for testing. That's where validation starts from. Validation starts from you separating your data. Now, when you separate the data, you can then use the training fraction of your data to run your model training. Fit basically trains this model, a linear regression model that we created here, right? And runs it on the training data, right? And then you can then use it to try and predict the equivalent of the test data. That's what I did here. Okay, so you have these values, but these values don't mean anything. Like, what does it mean? So the best thing is for you to say, okay, let me calculate the error. So I calculate error based on training data, which is this Y train and X train. And then I can also calculate error based on the test data. So you can see that the test data error is slightly higher, 0.040, than the training data error, which is 0.0039, but it's not that much higher. So what this tells me is that, well, okay, it's probably very good at generalizing. So this is what we're talking about. When you compare the training error or training loss with the test loss, the training loss gives you an idea. So when we hear, um, what do you call it? Um, the overfit versus the bias versus variance, right? Variance is bias is like a situation where the training um, loss and the training loss is very low, so it is doing well on training value, but the test loss is very high. That's variance. Bias is when both are very low. That means it's not even learning anything. Okay. So I could have done single values, but I decided to kind of use a graphical. So my graphs here are showing you on the right-hand side is the performance of this model on training data, while on the left-hand side is the performance of this model on test data. The performance on training data is based on the losses, the loss, right? Or you can just do predict, while this is a performance on test data. So that this is how you can compare. And you see that in this case, it is equally bad on both. So the model is not good enough. But you see, in this case, this is an interesting case actually, where it's not doing very well on the training model, on the training data, but it's doing so much better on the test data. But that's probably because the test data is much less in quantity, right? But it does mean that this model is doing very well in terms of generalization. Okay, so the other ones you can also see the random forest regressor. You see how well it does on the training data. It should do very well on training data. That's the training data now. That's what you're using to train it. But on the test data, it's not doing so well. Um, so that's it, right? Take note that this is a particular context of a particular training data. And what is just telling me that none of these models is really good enough to fit this particular data, right? We need to look for better models. And if you had neural networks, you will see that neural networks would have given you much better, um, you know, um, performance, both on training and on test. We will do that when we start neural networks. I will revisit this problem again. So I think I'll end it at that point, because we've gone way, way, way beyond time. If there are any questions, please go ahead to ask.